Indian time, and I'm extremely happy to have Robert Cameron uh, from the Max Planck Institute for Solar System Research giving our colloquium today. Shomak unfortunately could not be there, so I'm going to do all this thing. Robert is a very well-known solar physicist. He originally was in Australia long time back, and then was a postdoc at Caltech, and then in Japan. And I see that he moved to the MPS almost 2 decades ago, and
Yes.
he's been there for quite some time and very well known to many of us in the audience. Although I'm seeing him for the first time, which is very surprising. So Robert is going to tell us all about the magnetic flux budgets of solar and stellar dynamos, and very much looking forward to it. Robert, please take it on.
Okay, so if we're interested in the sun, or if we're interested in space weather, there's many phenomenally beautiful things to see, and they're all driven by the magnetic field, which comes from inside the sun. And space weather and the CMEs, all have rather short time periods compared to the 11-year magnetic cycle. And so here we have solar activity measured by the sunspot number as a function of time from 1700, so not long after the invention of the telescope, through to 2021. And we see there's an 11-year periodicity, but we also see that this periodicity is far from periodic. Sometimes we have huge cycles, sometimes we have very small cycles. And what we would like to do is to understand and maybe even be able to predict the activity or what determines this level. And then this would allow us to understand the solar dynamo and understand the fundamental driver for all of space weather. Fortunately, we have observations. So these are Mount Wilson line of sight observations of the magnetic field at the solar surface. And if you look at this magnetic field, you can see magnetic flux popping up onto the surface. So the blue is magnetic field pointing towards us. The red is magnetic field pointing away from us. We're seeing the rotation of the sun. We're seeing stuff pop up, and we're seeing polar fields at the top and bottom of the image. What is the actual physical quantity we see? Well, we see the line of sight of field. So that's with the observer, we sit out at the Earth, and we're seeing if we look at the center of the disk, the radial field, which is just rotated or emerges underneath the pixel we observe. If we look at the limbs, then we see something different. So at the limb, the line of sight component of the field corresponds to the phi component of the field. If we look at one limb, and if we look at the other limb, then it's the minus phi component. So here, phi component of the field points towards us. Here, phi component of the field points away from us. And so by looking and recording, it says we have 4 cycles of these magnetic images. We can average them in time, and we can make a map of the magnetic field over the radial field, the colloidal field, as a function of latitude and time, in this case from 1976 to 2017, or we can have the phi component of the field. So again, it's a function of latitude and time. We get this basically by observing near the center of the disk, so along the meridian, and we get this by observing at either the east or west limb. And we fit to sines and cosines to get the actual value for the flux. So we can do this for the for the Wilcox Solar Observatory. You can make similar maps for the Mount Wilson Observatory, which made similar measurements. Actually, these measurements are from the Mount Wilson Observatory. The Wilcox Solar Observatory is lower resolution. And what you see is, if you compare these, they match very well. This, of course, just means we're looking at the same sun, but it also means we're not dominated by either noise or instrumental effects. So we can measure the colloidal and toroidal field at the surface of the sun. The radial component of the field, the colloidal component of the field, is basically magnetic flux, which is either sticking out of the surface or going into the surface. The phi component of the field corresponds to flux emergence. And so you can imagine we sit out here, we observe the photosphere at the limb. So the photosphere is now parallel with the line of sight, and we're imagining a flux tube emerging through it. As the flux tube emerges, the field in the photosphere will have a component which is pointing towards the observer. And because it's pointing towards the observer, it's in the observer's line of sight, and we observe the phi component of the field. So this map is actually a map of flux emergence which preferentially obeys Hale's law. So the blue means it's emerging with one sense for Hale's polarity law. So the active regions we know merge with Hale's polarity law. Karen Harvey in the 90s showed that ephemeral regions at high latitude at earlier phases in the cycle also emerge with a preference for Hale's law. So this is flux emergence, preference for Hale's law. This is toroidal flux, which is leaking out of the solar interior through a flux emergence process. If we look at this for one more moment, another thing which is noteworthy is that here, when activity is strongest, when activity is strongest in one hemisphere, we're dominated by one polarity. So near solar maximum, for example, about 1993, in the northern hemisphere, the toroidal field is all blue. And this motivates us to ask, since this is flux which is leaking out from the solar interior, it motivates us to ask two questions. One is how much flux is being lost through this mechanism, through the leaking out through the surface, through flux emergence. And the second question is how much net toroidal flux is actually being generated. And so this is a question of the toroidal flux balance. And we're going to address this equation by looking at the induction equation and applying Stokes' theorem. So the induction equation tells us how the time evolution of B is related to the curl of the cross product between velocity and the magnetic field with a diffuser term. Applying Stokes' theorem, we get the time rate of change of the net flux through some surface in terms of a line integral. We can neglect, we don't have to, but it's doesn't make any difference because to keep it. So we can neglect this, the effect of the diffusion. So this is not turbulent diffusion I'm talking about. This is microscopic diffusion, and the microscopic diffusion is extremely small. And it's going to be useful in a minute for me to introduce and talk about the axisymmetric component of the field and the non-axisymmetric components of the field. And so I'll use the brackets to indicate the axisymmetric component and the primes with little u and little b to indicate the non-axisymmetric components. So we form the budget by looking at of the toroidal flux, we're looking at how much toroidal flux is generated in or the time evolution of the toroidal flux through the surface, which is the convection zone, the northern hemisphere. And so this will be the time derivative of the flux is equal to, by Stokes' theorem, this line integral. The large-scale field, large-scale components, and small-scale components. In the interior, so beneath the base of the convection zone, the 22-year solar cycle magnetic fields do not penetrate, and so the large scale B is small. The fluctuating component of B will also be small, and so there's no contribution from the interior. To evaluate the other components, it's useful to move into a coordinate system which rotates with the equator. And we can do this because differential rotation at the equator is small compared to the differential rotation, for example, with latitude. So we're moving into a coordinate system and rotating with the equator, actually with the equator at the surface, but this is essentially the same rotation rate with depth. And as soon as we do this, then the large-scale velocity, the u phi and the u theta components at the equator vanish by symmetry. And because these are the only components, because the UR doesn't contribute to this integral, so we do expect it to be a radial component to the velocity, but the radial component, because here your dl will also be in the radial direction, the cross product between a radial component and something else will make this perpendicular to the radial direction. And then if we take the dot product with the radial direction, we end up with 0. So along the equator, there's no contribution from this integral. Along the axis, there's no contribution because here, again, the large scale U vanishes. So we're only left with contribution from along the photosphere of the large scale field. And this contribution from the axisymmetric, or the large scale axisymmetric is a better word, contribution, is given by u cross b dot dl, where dl is in the theta direction. You can write this out explicitly because we know what the velocity is, and we observe the magnetic field. So this is an observable quantity at the surface. It's a differential rotation in the frame where we're rotating at the equatorial rate times the surface magnetic field. As I said, these are observables. We observe the differential rotation. It looks something like this. And we observe the magnetic field. The axisymmetric component of the magnetic field is just what we discussed before when we were talking about the colloidal field. So we have measurements of it as a function of time for the last 4 cycles, and as a function of latitude. So we can do this integral, and we find values of about 5 to 8 times 10 to 23 Maxwells. This is the contribution to the time rate of change of the flux in the northern hemisphere by basically the winding up of magnetic field due to latitudinal differential rotation. Field threading through the surface and concentrated, and the effect is really coming because of this multiplication with the differential rotation from the magnetic field near the poles at minimum. The other term which we can evaluate is the small scale the terms coming from the small scale magnetic field or the non-axisymmetric velocity and magnetic field perturbations. When you take the cross product of these, even though this is not axisymmetric and this is not axisymmetric, the cross product can have a component which is axisymmetric, and we need to evaluate this. And it turns out this is the type of thing observers really can evaluate. Observers like looking at the small scale magnetic field, and observers like looking at velocity fields. It turns out that this term, the small u dash plus small b dash term, is dominated, completely dominated by flux emergence. So as flux emerges for the surface, small scale phi component of the field is carried through the surface by a small scale radial velocity. So it's a correlation between the radial velocity and the emerging flux, and the phi component of the flux during emergence, which gives rise to the flux source. So flux emergence through the photosphere carries toroidal flux from the interior into the solar atmosphere. So this is the loss term. And you can evaluate this because people like Hagner and Karen Harvey evaluated all the terms you need to do this in the 1990s, early 2000s. And it turns out to be about 3.3 times 10 to the 23 Maxwell's per cycle per hemisphere. And so we generate through the omega effect, the winding up of the surface radial magnetic field lines spreading from the surface by the differential rotation, about 5 to 8 times 10 to the 20 Maxwell's per cycle per hemisphere. And we lose through flux emergence about 3.3 times 10 to the 23 Maxwell's per cycle per hemisphere. There's some degree of uncertainty in both of these numbers, but what you should understand is that most of the flux we lose through flux emergence, or slightly more than the flux we lose through flux emergence, is what we expect to have been generated by the winding up of the field threading through the surface by differential rotation. So this is the toroidal flux balance. It's basically the field we lose due to emergence, which is 0.3, 0.4 times 10 to 23 Maxwells per year, is balanced by the amount we generate through the omega effect. So the winding up of field lines which poke through the surface. And this is sort of a 0D representation of this flux balance. So we generate flux, and at some point later in time we lose it, and we just keep going around and around in circles. It's a noisy, this process, this is clearly not perfect cycles, and that's because there's noise to the dynamo process. We can also look at the colloidal flux budget, which is a little bit easier because everything involved in it happens at the surface. So the reason we're interested in I'll just go back a few slides. The reason we're interested in the colloidal flux budget is because this field in the poles, which is generating the toroidal field of the next cycle, is basically all the flux in that hemisphere. So at the end of the cycle, when things are really most important, the amplitude of the field is determined by how much net colloidal flux you have threading through the surface of the sun in that hemisphere. So again, all we need to know is what determines the strength of the polar fields, and this is determined by how much net flux is in the hemisphere. And so this is the colloidal flux balance, how much net flux is in a hemisphere. And the time rate of change of it, according to the induction equation and Stokes theorem, is given by this surface integral. This is an integral along the equator at the solar surface. And everything here is observable. We can observe the flux, the total flux in the northern hemisphere. We can observe radial velocities carrying a feeder component of the magnetic field through the surface, and we can observe that latitudinal motions carrying radial field across the equator. The observations for the first term, the URB feeder term, corresponds to flux emergence across the equator. And here's a nice example from 1979, where we have a large active region emerging across the equator. And in terms of effect, we need to remember that the polar fields correspond to the flux of one or two large active regions only. Therefore, having an active region which emerges directly across the equator is extremely effective at changing the net flux in each hemisphere. In this case, most of the positive white flux will end up in the northern hemisphere's pole, and most of the black flux will end up in the south polar fields. So flux emergence across the equator is an important term, but it's a completely random term. So there's no known way to predict, or no statistical indication at all, whether this would emerge with white in the northern hemisphere and black in the southern hemisphere, or black in the northern hemisphere and white in the southern hemisphere. And so this is a large source of noise in the solar dynamo process. It corresponds to noise introduced by highly tilted active regions across or close to the solar equator. The more systematic term comes from the U theta BR. So this is material being carried across the equator with a radial field by a latitudinal motion. So you can imagine in 1990, in the northern hemisphere, random motions, so supergranular motions, act on the blue field, which is in the positive field, the blue field, which is in the northern hemisphere, preferentially dragging across the equator. So the blue field will be moved towards the equator, towards the pole, just by random convective motions, supergranulation, granular motions. But because the blue polarity is closer to the equator in the northern hemisphere, more of it will be transported across the equator than the red. The red, however, will be transported from the southern hemisphere to the northern hemisphere. And the net result of this is the northern hemisphere will lose a little bit of blue, gain a little bit of red. And so it's 1990, changes into 1996, changes towards 2000. We see the polar fields become red, dominated by a negative polarity. The reason we have a little bit more blue near the equator in 1990 in the northern hemisphere is because of flux emergence. So we've had flux emergences which obeys Joy's law, and Joy's law essentially says that the leading polarity emerges slightly closer to the equator. Because of Hale's law, that leading polarity, in this case, will have a positive polarity, and so the positive polarity emerges a little bit closer to the equator than the northern polarity. You can test this because we have very good observations. You measure all the tilt angles of emerging active regions. You put them into the model where we have flux emergences plus this diffusive term. And what you find is it very nicely reproduces the observations. And this is not only in overall amplitude, but also in some of the details. So we understand and observationally very nicely reproduce the observations by applying Stokes' theorem to the induction equation. And the basic point again is that the change in flux at the pole corresponds to flux carried across the equator. And Joyce's law is essential to this process because Joyce's law is what causes the leading polarity in one cycle. All the leading spots have the same polarity to be slightly closer to the equator than the trailing polarity. We're not sure where Joyce's law is coming from, and this is an interesting open question for this type of analysis. We can now look at so we've seen before the top panel, which is the toroidal flux balance. We can now look at the colloidal flux balance. And in this case, basically the flux in the northern hemisphere, or no, in this case in the southern hemisphere, because I'm from Australia. The flux in the southern hemisphere, so we're only looking at the flux in the southern hemisphere. We multiply the flux in the northern hemisphere by 0. The net flux is given on the x-axis. It's in units of 10 to 22 Maxwells. And the generation term, which is Joyce's law times how close you are to the equator, times the subsurface, the flux emergence, which is based upon the subsurface flux and the emergence velocity, gives you the polar field generation, colloidal field generation. And the colloidal field at the end of the cycle ends up at the poles. This process is genuinely noisy. It's noisy because the flux emergence, sometimes we have very large active regions emerging just across the equator. I want to now move to this budgets and stellar dynamos, and I'm going to begin with an old picture. This is a modified version of Sarah and Brandenburg, and you'll notice lots of stars. There's 2 branches, an active and an inactive branch, and the sun sits here. A number of stars have activity on both branches, and for the rest of this talk, I'll concentrate on 3 stars. The sun, so pretty, 61 sig A, and Epsilon Eridani. These are K2V, K5V, and G2V stars. So there's slightly lower mass than the sun. The rotation period of the Epsilon Eridani is significantly faster, and of 61 sig A is a little bit slow. The first thing I want to convince you is that the large scale, so the axisymmetric field, the axisymmetric field averaged in each hemisphere. So this is the phi component of the field. So the blue and green curves show the phi component of the field averaged in latitude and longitude in one hemisphere. So in the hemisphere on the sun, the northern hemisphere, and in the other stars, the hemisphere pointing towards the Earth, or slightly pointing towards the Earth. And you'll see the blue curve and the green curve make for the sun a nice 11-year picture. So if we concentrate at the sun, at the top panel, this is just the sun, all the data from Mount Wilson, and I've just plotted the magnetic field, boom, 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 as a function of time. This phi component can be positive or negative. So the mean field in each hemisphere, mean phi component of the field, can be positive, it can be negative. And so if it's negative, I've just plotted it in green. So I've flipped it and plotted it in green. So this is why this plot only has positive values, because when it should be negative, I've just changed the color and made it positive. The red curve is the chromospheric activity. So this is solar activity measured by proxy, which comes from the chromosphere. And so what we see is chromospheric activity. We see an 11-year cycle, and this 11-year cycle is coming from the phi component of the field, which is basically flux emergence. There's a slight shift in time, not critical. The left panel show the full time period for which we have available chromospheric activity, and the right panel shows just a period overlapping with where we have magnetic activity. Of course, we see the sun with exquisite resolution. Other stars we're not going to see with such high resolution. So we've taken the data and we've decomposed it into spherical harmonics, and we've only kept the low order spherical harmonics. And this is shown in the second set of panels. So this is what the top panel would look like if we could only see the sun with spherical harmonics less than or equal to 3. The picture is very, very similar. So the chromospheric X-index is completely unchanged. It's a global index. What changes is the blue and the green curves. They're slightly weaker because we've lost some of the spherical harmonics, but because we're looking at an average over latitude and longitude, the change is actually not so much. We now turn to 61 sig A, 61 sig B, and the main difference we see with 61 sig A is we see a cycle, it's noisy, the solar cycle is also noisy. We have very little magnetic data. We've only got 2 activity cycles, which corresponds to 1 full magnetic cycle. But if you look just for the period where we have overlapping magnetic and activity data, then it looks like the sun did. We see a slight offshift in time, but we have a magnetic cycle which flips sign, and when the activity is high, the amount of flux emergence as measured by the average phi component of the field in the hemisphere is large. When we look at epsilon Eridani, we see a slightly different story. So we still have variations, and if we look at the time when we have only the magnetic and the magnetic activity data, so on the right panel, then what we see is, again, we see nice cycles, but in this case, the magnetic polarity only flips once very early, and then it becomes large, and then becomes to decrease again. And the activity cycles shown in red now has the same period as the blue curve. Here, if we go back up to the sun, the 11-year solar cycle corresponds to a 22-year magnetic period, because we go blue in one cycle, and then we're negative in the next cycle, which is shown in green, and then only then do we go back to blue. So the magnetic period is twice the cycle period. But here, in the case of epsilon Eridani, the magnetic period and the activity cycle period are the same. And this is because the magnetic field isn't actually flipping sign during this period. And it's not flipping sine because it's a superposition of a short-term cycle with a period of about 3 years and a much longer time scale cycle with a period of about 20 years or 14 years. So if we go back up to epsilon Eridani, we have two cycles. One cycle has a period of about 14 years in its chromospheric activity. This is chromospheric activity period. And it has, and the magnetic cycle, so if you go back to here and you fit this behavior, you find it corresponds to the sum of two sine curves. So the dashed line, the solid blue line here is a fit to the data. In the case of epsilon Eridani, I've used a fit which is two sine curves. For the sun and for 661A, a single sine curve was enough. But for epsilon Eridani, I required two sine curves, and they had a period of about 28 years and a period of about 3 years. And the 28-year period is up here. Half of it gives you about 13, which is the yellow, which is this dot. And so this is a long-term cycle, and the short-term cycle of 3 years is this activity cycle. So I need to have two sine curves to fit the magnetic activity and the periods of what you would expect from the chromospheric activity. So what this tells you is that the cycle of epsilon Eridani, these two cycles are both real and they're both magnetic cycles. It's not, in the case of the sun, for example, we have many periodicities detected in the data corresponding to basically random fluctuations. With the case of epsilon Eridani, these two cycles are both clearly indicated to be magnetic cycles from the fact that basically during this period from 2010 to 2020, the sign of the toroidal field for the northern hemisphere doesn't vanish. These data, of course, are taken from ZDI maps. So I should have mentioned at the beginning, so the magnetic field for the sun we get directly from resolved measurements of the magnetic field, and these measurements come from ZDI, Zeeman Doppler imaging of these stars. Now, just like for the sun, we can continue and we can look at the flux balance. So we can say, where does this toroidal flux come from? So this is a net toroidal flux leaking out from the surface of the star. Where does it come from? On the sun, we had a match between the amount which was generated by the differential rotation acting on the surface magnetic field and the amount which was leaking out through the solar surface. And this match we can see in this form, where we have the amount generated in orange and the amount we lose in green. And you'll see these axes are the same, and this is just telling you that we produce slightly more than we lose. You can do the sun low resolution, and the picture does not change very much, so explained above. And you can now do the same for 61 sig A and epsilon Eridani. And the reason you can do this is because Zeeman Doppler imaging gives us not only the B5 component, but also the, which is necessary for the green curve, but also the BR curve, BR, which is necessary for evaluating the surface term. We also need the differential rotation, Zeeman Doppler imaging, and other measurements for these two stars, both 61 sig A and epsilon Eridani, indicates that the differential rotation is similar to the sun. And so for this estimate, we've just used solar differential rotation. Of course, you need to be concerned with noise. And so we've estimated in the light green with these two error bars in 2016, they took a number of measurements, 3 measurements closely spaced in time, and these allow us to estimate the error bars because there should have been not very much variation. And what we see is the errors are small compared to the variations we're seeing. So basically, we don't need to worry about the errors. At least the random errors when we're doing this analysis. They're small compared to the signal we're looking at. And we can do the same for epsilon Eridani. And again, we see there's, to match the data, we need to combine two cycles, a long-term cycle, which is shown in the dash curve, plus a 3-year cycle, which then allows us to reproduce the data. So both, so the cycle period is seen in the B phi loss term, it's seen in the B phi generation term, and it's seen in the chromospheric activity term. Of course, nothing what I've talked about so far is a complete dynamo model, and this is because we need to transport the field. So if you look at where the field is generated by the winding up of differential rotation, it will be at about 55 degrees, whereas flux emergence emerges at about 50 degrees, 35 to 5 degrees, depending on the time of the cycle. So we need some transport mechanism. We also need the transport mechanism. So we say it's a flux which crosses the equator, which is important, but the flux has to be transported to the poles where it can be acted on by the differential rotation. So to make a complete transport model, a complete dynamo model, we need to include transport processes. The transport of the fields from the equator to the pole, this is observed. This all happens at the surface, and people have been looking there for many years. At least we have synoptic observations going back over 4 cycles. And this gives rise to the surface flux transport model, which says after emergence, the magnetic field is acted on essentially as a passive transport. So this is just how you evolve, or how the surface magnetic field evolves after emergence. We don't directly observe the transport of the magnetic field beneath the base of the convection zone, and therefore we end up with more terms. Some of the transport process could be small scale correlations between the small scale magnetic field and velocity field, or it could be the large scale velocity field and large scale magnetic field. The large scale magnetic field, we can infer at least how much flux is involved, and we can measure the strength of the meridional flow near the base of the convection zone. So we can measure U phi, and we can estimate how much flux is involved for the B phi. And it turns out that if the magnetic flux is stored in the lower half of the convection zone, then this terms are certainly important, and they're large enough to completely explain the transport we see. However, these terms could still be important. So let me skip that. Let me just say, yeah, so we can put all this together into a model. So the equation we have for B and the equation we had for A. The equation for A, everything is known. The equation for B, a little bit more uncertain. We have to put in the meridional flow, which we have measurements from helioseismology, but the exact value for V0 depends on where we think the flux is stored. And we have to put in a decay time, but this time is actually constrained by observations. In particular, we need to introduce this alpha effect. And this alpha effect is Joy's law, and we do not have a good understanding of what Joy's law is coming from. In any case, we can make a model with only 1 or 2 free parameters, and then we can compare the observations with the model, and we find a good match. So this is a radial field at the surface, and this is a subsurface toroidal field. This is the observed toroidal field at the surface, and this is the subsurface toroidal field of the model. The model doesn't predict the toroidal field at the surface, it only predicts the toroidal field beneath the surface. And this is just when I saturate the toroidal field to show you more so the structure goes all the way up to the high latitudes. You can also test the model by looking at the cosmogenic data and the sunspot number, which has been observed for several hundred years, and the cosmogenic isotopes, which have been observed for thousands of years, and you find the model does a nice reproduction of the observations. So observations, sunspot numbers are green, the blue is the cosmogenic isotopes, and the model is shown in red. And so here's some nice reproduction, but you'd get the same qualitatively the same reproduction even if you consider the simplest model you can imagine, which is a Hopf bifurcation, where we just add some noise into the stochastic to make the Hopf bifurcation as a stochastic ODE via this white noise term in the ODE. So this is just a power spectrum. So the shown here is a power spectra of the amplitude of X, where X is just a scalar number which satisfy this this stochastic ODE. So matching this observation, you can do really, really simply with the simplest model possible. So let me just run through the conclusions. So we've discussed the toroidal flux balance, what we create by winding up of the field at the surface by latitudinal differential rotation, we lose through the flux emergence. This is true not only for the Sun, it's also true for Epsilon Eridani, the 61 sig A, and the 2 cycles of Epsilon Eridani. Both cycle periods reported for Epsilon Eridani are magnetic cycles. The change in the flux at the poles corresponds to flux carried across the equator. This is the toroidal flux budget. Flux transport at the surface observed. Helioseismology indicates an equatorial flow in the lower half of the convection zone. Flux transport is needed in the deep interior. Meridional flow fits, but turbulent effects could play a role. And I will stop talking and take questions.
Oh, thank you. Thank you very much, Robert, for a very interesting talk on this fluxes coming from observations. Yes, Durgesh, please go ahead.
Yeah, hi, Robert. Thanks for the nice talk. So, one thing you pointed out that the emergence of these new bipoles right at the equator plays a very important role in the way the cycle is shaping up. So, are there any statistics on that? And also, could you just repeat again that in what way exactly does it change the cycle behavior?
Yeah. So the question is okay. So if you want to know the strength of the next cycle, yeah, then you want to know how much flux is at the poles, because the polar field is what gets wound up to give you the next cycle. And this is why if you look, Wang and Sheely, for example, find a very strong correlation, proxies for the polar field and the strength of the next cycle. And this is understood because it's a winding up of this field which gives you the strength of the next cycle. So then you say, what determines the strength of the polar fields? Or how much flux gets into the polar fields? And the only way to get flux into the polar field is to transport flux across the equator. To transport flux across the equator, and boop, eventually at the end of the cycle is carried to the pole by the meridional circulation. So then you say how much flux gets across the equator. And this is very easy because, this is just, again, Stokes' theorem applied to the induction equation. And there's two terms. So it's U cross B dot dl. dl in this case is in the phi direction. It's the line at the surface at the equator. So it's purely in the phi direction. And then you look at the, you do this cross product, and you find it's URB theta minus U theta BR. And this one corresponds to flux emergence at the equator. It's a radial velocity carrying a latitudinal component of the field across the equator. And if you look at this image, for example, and you imagine this is a flux tube emerging from below, what happens is it's carrying flux pointing north-south, radially upwards across the equator. And this is why flux emergence at the equator is so important. Of course, if you happen just a little bit away from the equator, it's still important. And it's important because
Right, the other top.
Yeah, but because you then got a lot of flux near the equator, which can be of one polarity, which can be carried across the equator by the turbulent motions. And there's a number of people who have looked at this, including Petrové and his group, and that's what gives you this term. So if you emerge near the equator, you're extremely efficient in transporting stuff across the equator. If you emerge even at 20 degrees, it's very, very difficult for any of that flux to get across the equator. So it's only emergencies close to the equator which make a difference for the polar fields and therefore the strength of the next cycle.
Okay. Yeah, thanks.
Axel, please go ahead.
Hi, Robert. Thanks very much for your very interesting talk. I had three small questions. First one, flux submergence, you probably imply is small or absent. Second question, you were about Joyce's law, you were saying it is unclear where it comes from. Usually in the literature, people are talking about the Coriolis force. I can see another candidate, namely the shear. So could you comment on that? And then finally, about epsilon Eridani, you were saying it has two cycles, which is indeed the case. Do you have any idea what could cause these two cycles? Is there any idea where that comes from?
So let me do them one by one. So can you ask the first one again?
Submergence.
Submergence. So submergence is certainly happening, certainly important. But the point is, so the point is, we have very good observational evidence. So after emergence, the surface flux transport model works. And it basically says after emergence, they act as passive quarks. If two quarks of opposite polarity come close enough together, they submerge and disappear. There's no question about that. And this gets rid of almost all the flux in the system. However, the remaining flux moves a little bit further apart. So the random motions push a lot of it together, but the stuff it doesn't push together, some of it goes further and further apart in longitude. And it turns out there's a conserved quantity, which is the product of the distance it's been separated times the amount of flux. And this tells you that the flux lost due to a flux emergence rate is a conserved quantity. So even though most of the flux reconnects and goes back beneath the surface, the small fraction which has drifted further and further in longitude has drifted exactly the correct amount to balance the fact that you've had some reconnection. And this is dealt with in the Cameron and Schuster 2020 paper, and you can visualize it if you think of the two Gaussians initially with some separation between them, and the Gaussians just get broader and broader as time goes on. Your submergence is the overlapping region of these two Gaussians, but because the system is linear, it doesn't matter for the calculation of the net total flux, which is asked. The second question was
Joyce's law. Yes, Joyce's law.
So Joyce's law, whatever's happening, Joyce's law is coming from the Coriolis force. It's coming from the Coriolis force acting on those due to the emergence, or those of the convection, or those which set up the differential rotation and therefore the shear. So there's no question the Coriolis force is implicated, but which of those three flows it's acting on, or whether there's other possibilities as well, this is what we don't know. And this is what's actually hard from an observational or theoretical to get a good grasp on, which is the fundamental flows in which the Cohen's force are operating, which is fundamental to the Joyce law. Your third question?
Epsilon Eridani, the two cycles, where they come from.
Yes. So what we can show is that it's surface field, which is generating in both cases the large-scale toroidal field, and it's the large-scale toroidal field, the net toroidal field in the hemisphere, which is emerging and which is giving rise to the cycle. And in this case, and so in this sense, they both appear to be consistent with the Babcock-Leighton framework. A possible comparison with the Sun would be to say they correspond to a quadrupole and dipole mode of the Babcock-Leighton dynamo.
But they are so far apart. Normally, if you have a quadrupole and dipole, they would be close together, right? The frequencies.
No. So in the Babcock-Leighton framework, even on the Sun, you have a period of 22 years and a period of 14 years. And Manfred showed this in a paper in maybe 2018. But anyway, for the Sun, they're not even close, particularly close, 22 and 14. But in principle, you expect that to depend on where the flux emerges. So as flux emerges at higher latitudes, the naive expectation would be for the dynamo period of the quadrupole mode to get shorter. And I think we've looked at that as well in the Babcock-Leighton parameter study. But in part, it depends also on what you put into your model. But if you put in, for the solar dynamo case, what we know is the physics from observations, then at least for the Sun, you get periods of 22 and 14, which are not so close.
Okay, and that's because of Babcock-Leighton specialities, you're saying. Because normally mean field dynamos, I don't think have that.
Yeah, so the Babcock-Leighton is at least consistent with a type of mean field. So in the Babcock-Leighton framework, so the time is set in part by the time so in part it's set by the actually the transport processes. So the point is, which we want to show. Yeah, this one. So on the bottom panel, can you see my mouse or not?
Sorry, we lost your slides. Okay.
Okay. Half a second. Just one more second.
Yeah, that's fine.
Can you see it now?
Yes.
Yeah.
Yeah.
Okay. So and can you see my mouse?
Yes.
Okay. So this panel is how effective flux emergence is at transporting field across the equator. And for the dipole mode, you need to basically have emergences within plus or minus 10, plus or minus 15 degrees latitude to get anything across the equator. So if you have an emergence at latitude 50 degrees or even 30 degrees, both polarities get transported to the pole. And for a dipole mode, this is just not effective at all. But even an emergence at 30 degrees or 20 degrees can still be important for a quadrupole mode, because there you don't need to get the flux across the equator. So in this picture, for the colloidal field, it's only getting flux across the equator, which is important, and this is dominated by low latitude emergences, and therefore you need to advect your toroidal field from 50 degrees, where it's mainly produced, to low latitudes where it emerges. And this is done by some transport process, quite possibly the meridian of circulation in the bottom half of the convection zone. And this is what sets the period of the dynamo. And the quadrupole mode, you don't need to transport it all the way to the equator, and so the period can be shorter.
I see.
It's this difference of the quadrupole and the dipole mode in a situation where the dipole mode is really about transporting flux across the equator, and therefore it's really about transporting the flux towards the equator.
Okay, great. Thank you very much for the answers.
Okay.
Thank you. Any more questions for Robert? I had some questions, two questions actually. One, remarkable that you can just deal with surface observations.
Yes.
And make a dynamo model out of everything.
Yeah. So when I was asked 13 years ago whether we could predict the cycle, it was clear to me that the answer was no. But because the chances at the surface is what's dominating the story a priori, you would think would be very low. And I certainly thought the probability of being able to predict it would be extremely low. You can imagine many scenarios where you simply cannot predict from the surface what's going on at all. However, the observations, there's very strong evidence that the polar fields are correlated with the strength of the next cycle. And then when you calculate how much toroidal field is being calculated by the surface fields we see and by the differential rotation we see, then you find it's a large amount of flux. It's just a little bit more than we actually need to produce to be. So yeah, I agree. It's extremely surprising, but this is what we have. And partly, yeah. Okay, so just let me make one more comment.
Yes.
Yeah, just let me make one more comment. It's partly because if you look at the differential rotation, it's more or less featureless. The sun is really quite boring. If there were features in here, or strong features, then certainly we could have other types of dynamo. But the sun has rotated to the point where it's barely maintaining dynamo action. It's apparently the differential rotation doesn't have very strong features, and therefore we're left with the simplest thing which we could get, which is a backward-laden type mechanism.
The other question I had was, you had these sources, but there was also some alpha term, which came from where? I mean, that didn't come from observations, right?
Yeah, so the alpha which goes into the model is the tilt, or what goes into the...
that came from the tilt, the Joyce law.
It's Joyce law. So in the observations, what the observations show is that the polar fields produce enough flux to explain the solar cycle and are strongly correlated with the strength of the next cycle. Therefore, the polar fields are observationally implicated as being extremely important. The polar fields, you can trace them back to flux emergences, which are tilted. So it's a tilted flux emergence, which is the alpha effect. And so the question is, why do we have these emergences which are tilted? And this is hard at the moment to say. I'm not sure. Is Coriolis force acting on something?
Yeah, the last thing which I wondered about was, of course, favorite for both Axel and myself, magnetic helicity. Because your induction equation conserves everything.
Yeah.
You even put eta to 0.
Yeah.
So does your dynamo somewhere conserve magnetic helicity, and what's happening to that?
Okay, so I think there's nice work by, I think there's a paper by Berger, which is corresponding to this one, but my understanding is as follows. So when I'm talking about flux emergence, I'm talking about toroidal field, which is being removed through the photosphere. Yeah, and this will certainly also be transporting helicity. So flux emergence, even if it was not tilted, even if it was a nice simple loop, I've then taken the field line, a phi component of the field line, and I've removed it outside of the photosphere. So I've changed the helicity by moving a loop outside of the, so I've got field lines which go for the pole, for the equator, and to the other pole. Now I've got field lines which wrap around. So I've got some mutual helicity. And now I'm removing this field line out for the surface. So the flux emergence here removes the helicity, which...
Right.
Yeah.
Yeah, certainly very interesting, and I will look at these papers with a bit more care now, I think. Thank you. Thank you very much. Yeah. Any other last questions for Robert before we let him go for his lunch? One more. Yes, Durgesh.
Yeah, Robert, I thought I'd ask you this. People keep mentioning this magnetic flux submergence and magnetic flux cancellations. Are these two different things or are the same thing? Or if there is any difference, is there any observational thing which we can see and check if it is cancellations or submergence?
So this question, I guess, depends upon where the reconnection happens, whether it occurs slightly above or beneath the surface. And this isn't something I've thought about in the context of this talk. It's so in both cases they will remove. So I guess it's a submergence if you reconnect above the surface and then you retract beneath the surface, and it will be a cancellation if you reconnect right at the height of the surface. And this is sort of not, I haven't considered that in the context of this talk. This is something probably we considered in the context of Miriam simulations, but I do not remember the answer at the moment.
Yeah, the reason is that all these, like you mentioned, coronal mass ejections and flux cancellations comes in, and all the observations are based on the photosphere, HMI or MDI magnetic field data, right? So, so it's not really clear that if it is a submergence or a cancellation, because we are all observing at the photosphere, so it's not really clear where the
yeah. And this is why for those type of questions we need multi-height, more multi-height diagnostics. And I think people are working on it, but that's hard.
Right. Okay. Thanks.
Okay, thank you. Thanks a lot for a wonderful talk and for being with us and for answering all our questions.
It was pleasure. Not as much pleasure it would have been if I was actually there.
Well, yes, Durgesh and Nishant would have taken you out somewhere. Absolutely. Thank you very much, Robert.
Robert has been at IUC a couple of times, I think, or once.
Yes, I've been there once or twice, maybe, I don't know.
So that's how
it's a very nice place. Yeah, that's why I'm missing it. If I hadn't been there, I wouldn't be missing it so much.
Okay, on behalf of everybody, let me clap. And thanks a lot.
Bye.
Okay, bye.
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 We can shut down, Santosh.